All right. Now we can now begin. So we were talking about the two-dimensional discrete time or discrete space Fourier transform and its properties. And previously, I told you that I would look for some internet resources which can show how the Fourier transforms of some certain shapes may look like. I found a few of those and I want to show them to you. They are very important. They are so critical that when you look at an image, the same is valid for DFT, two-dimensional DFT or FFT as well. It's essentially corresponding to one segment of an image and its Fourier transform from -pi to pi in both dimensions or something like that, similar to that one. So essentially it's the same. So it's very good to develop an intuition regarding how the Fourier transform will be for some certain specific shapes and their descriptors. Because in many cases, the pattern recognition of from images or some feature extraction from images will be done in the Fourier domain. So by just looking at the Fourier transform of something, you should be understanding what we have inside the image or what component of the image produces what in the Fourier transform. Okay, that's an important skill, and I strongly recommend that you have it. Now, maybe I have to refresh. So, yes, I'm refreshing this thing that I want to share, but it's just showing blank now. I hope it gets corrected. I will try to load it again. And if it cannot load, you know, it would be a pity. Then I may have to download it and then show it from a PDF reader or something like that. Come on. Now let me try to show it from a PDF viewer if it can. It says it is downloading. Yeah, come on, come on, come on. Come on, come on, come on. Yes, yes, we have it. I can do it from here. In fact, it's better to do it from here because I can annotate by pencil on this one. Now, yes, this is where I want to start from. Okay. Now, the image is the grayscale one, the large one that we have. Okay, that is the wave. Now, if you have this kind of a wave in the image, as we have mentioned before, you can just visualize it in 3 dimensions. You will notice the wave. The whiter or brighter portions correspond to higher magnitudes, and the dark portions correspond to values closer to 0. So in order to plot it using MATLAB, for example, or show it as an image, you have to just move your function upwards in value in such a way that the minimum value becomes 0 and the maximum value may become something like 255 or something if it is 8-bit image visualization. Image showing tools in MATLAB, for instance, cannot show negative values, or it may behave erroneously. That is something that you don't want. So just bias or shift your values upwards so that the minimum value becomes 0. But anyway, we understand the image. This is the image that we have. And now look at the Fourier transform, which is here. This one. As you see, the Fourier transform is consisting of 2 impulses. That's brilliant, because those 2 impulses would mean that there is a cosine. And what is the direction of the cosine? The direction of the cosine is like this. Okay, it's essentially this direction that we have. They are aligned. Okay, this is how we come up with the Fourier transform expressions of images. If it's the sinusoid like the one I show you, of course I'm showing you only a crop of that. And its Fourier transform is consisting of two impulses. And if it is a discrete time image that we have, then it means these two impulses that we have, let me show them in red, this one and this one, these two red points will be repeated around 2 pi, horizontally around 4 pi, or vertically around 2 pi, minus 2 pi, 2 pi by 2 pi in 2 dimensions, etc. So this thing is also 2 pi periodic. All right. So this is a critical observation. Another critical observation from this wave and its Fourier transform is that if the wave period is larger and therefore the frequency is smaller, therefore that is, if it's a slower wave, okay, then these two red dots come together. Okay, they come nearby one another, and if they get separated more, then it means the frequency is higher. Then this oscillation will be squeezed and denser, higher frequency oscillation. I don't know if this one has that kind of a thing. Yes, look at that one. Look at this. The image showing another direction like this, and that direction is actually this one here that we have. Those are aligned. And as you see, the two dots are separated more from one another, and therefore the wave is a higher frequency, more condensed wave. So by looking at the pulse points or higher peaks, if they are showing in pairs in your Fourier transform, you can see that there is actually an oscillation going on along that direction, something like this. This kind of a wave exists. Suppose that you have a noisy image or a distorted image. The distortion is like this. This wave is somehow, it has appeared on your image. It may happen to old images, old photographs, for instance. They may be smeared and it may have this kind of undesirable defect. So what are you going to do to make an image restoration? How can you restore the image? The thing that you have to do is find this oscillation on the Fourier transform, detect them first. You will certainly notice some peaks in your Fourier transform at these 2 points. But these peaks, apart from these peaks, there will be several other things. Of course, there will be a real actual Fourier transform. I'm only plotting the magnitude here. So you will detect this oscillation on the Fourier transform, and at that Fourier transform domain, what you need to do is you have to assign a reject filter, a band stop filter, in other words, like these two green boxes. And inside the green boxes, you make them zeros. This Adobe Flash is doing some nasty things. I'm sorry, I will be back in a minute. Yes. Maybe you don't even see that. On my computer, Adobe Flash is trying to do something. So anyway, here inside the boxes, you make them zeros. And when you make them zeros, these red peaks will vanish. They will go down to zero, and you will completely get rid of these waves from your image. They will go away, and whatever the backside of that, maybe there was a person, okay, like this, at the background with eyes, nose, etc., this person will appear and the wave will go away. That's how we remove undesirable things, by knowing their Fourier transforms. There may be other examples where there may be a line, okay? That line can be a scratch. So how do we get rid of that line on the Fourier axis? We may do similar things. We may want to detect that the effect of that line on the Fourier transform and remove that effect, and then take back the inverse Fourier transform, and that line will just go away from your image. That's how we do image restoration. Let's see some further example. Of course, if you go as close as possible to the frequency of pi, or pi by pi, it will become like this. And eventually it may arrive to 101010 pixel, which is still a wave. You can think of it like that, but it will look, you have to look very close to see the waves. So as you see, the frequency of this particular image is very high, therefore the points are very much separated, closer to the boundaries. The boundary is pi by pi, okay? Now, some other important Fourier transforms. This was the thing that I wanted to show you previously. If you have an image which is consisting of a rectangular box like this, the Fourier transform of that one will consist of sinc functions. Here you may notice that this doesn't really look like sinc because it's the absolute value of sinc. Look at that, it's the magnitude. Just to avoid phases and negative entities, we may just take a look at the magnitude. So this, let's see if I can do that. This wave actually is going downwards. It's like this, and then like that, and then like this, and then like that, etc. Of course, the highest peak is still there, but the lower one, which was here, is actually negatively oscillating like this. And you just see the oscillations horizontally, and the same thing happens vertically too. I will have to undo this because I don't want to spoil this beautiful image. This, when you look at it from the top, it will look like the right-hand side figure, which is here. That's a separable sinc shape that is happening horizontally and vertically, and it forms a grid. Now notice that the original image height is short and the width is large. So height is short. Look at the Fourier transform of that. It corresponds to a wider sinc because of this short rectangular height. What I'm saying is this size is small, therefore this size is large. Whereas this size is large, and therefore this size is small, because they are inversely proportional. If something is short in the image, it makes longer. It makes it longer in the Fourier transform, because it's like the impulse will make it all constant, the widest thing. The shortest image is the impulse, and the widest thing is all ones in the Fourier domain. And it is also direction sensitive. If it is horizontal or vertical or in any other direction, if something is shorter in the Fourier in one domain, it is longer in the other domain. In fact, you could say that these are inverses of one another. Like if the right-hand side is the image, the left-hand side would be its Fourier transform, or vice versa. They are, there is a dual property that is happening. So this is the sinc shape that we have, and these are the Fourier transformation expressions of what we come up with, which is two sinks. One sink is here, and the other sink is here. So we are multiplying two sinks in two directions, horizontal and vertical directions. However, if the shape is not this rectangular shape, if it is symmetric, then we will, of course, come up with something different. For example, this is a Gaussian, but it is isometric or isomorphic. I don't really recall the original or the correct English terminology for that. So it is a rotationally symmetric thing. Therefore, it is described as r in polar coordinates. It is fr comma theta, like this. And for all theta, there is only fr, where r squared is x squared plus y squared. It's the radius from, or the distance from the center. Then its Fourier transform will be the Fourier transform related to only r, which is the central direction, okay, directional distance from the origin. For x and y, we have omega 1 and omega 2, but for r, we have to find another terminology for the frequency corresponding to that. And the usual notation that is used in image processing is rho, the Greek letter. So that's why we are using f rho, which is the Fourier transform of f of r. Okay, and it looks like this. As you see, this the original f signal was rotationally symmetric, so its Fourier transform is also rotationally symmetric. The same thing should happen in a cylinder as well, because a cylinder is also rotationally symmetric. Therefore, its Fourier transform is also rotationally symmetric. But what is that rotationally symmetric thing? If you cut this from any angle, if you cut this one from any angle, like this, take a slice of it, you will notice that you will come up with a rectangular shape if you cut a slice from the center or from any other position, as a matter of fact. But from the center, it will give you a rectangle. And we know that the Fourier transform of that rectangle is a sink shape, and that sink shape appears at the same slice, at the same angle slice of the Fourier transform. So this is the sink that has been rotated to make it rotationally symmetric. And the shape that we have here is the shape that is also known as the sombrero or sombrero. I don't speak much Spanish or Mexican, but it's the Mexican hat shape. That's where the name comes from. Clearly, of course, it also has some mathematical or analytical ways of expressing things, and that is the Bessel function of the first order of the first kind, J1 of x, J1 of pi times a times rho, where a is the width of the original rectangular cylinder. So symmetric things will produce symmetric things in the other domain, symmetric shapes in the time or space, symmetric shapes in the Fourier transform. This is the 2D version of a sink, okay, a rotationally symmetric thing. Now, some other Fourier transform pairs that are also important, we have seen, we know, we can understand these things. The first one is the impulse in the center, a point. Therefore, its Fourier transform is 1, which will give you a uniform thing. All right. The inverse is also correct. For example, if the image is uniform, then its Fourier transform will be a point. So, for instance, if you want to change the overall bias or the intensity of an image. What will you do? You have to take a look at the DC coefficient, which is the 0, 0 coefficient in the Fourier transform, the sample in the center. That central point, you can just change it to any value which will shift your dynamic range of the image upwards or downwards. For example, if you make it 0, it means you're making a 0 mean image, which just normalizes everything around 0. All your data will be normalized around 0. The other one is containing 2 pulses, and the 2 pulses will give you a sinusoid, a wave function in the Fourier transform domain. If you rotate those 2 pulses, the wave function will rotate the same way. So the angle that you rotate your image, its Fourier transform is rotated by exactly the same angle. That is a very important and critical property that you have to always keep in your minds. Now, an interesting thing, this one. We used to have Java applets, and I used to illustrate this very well. But nowadays, the modern browsers, nothing supports the Java applets, and I cannot really show this to you. But this is interesting. The interesting thing is as follows. We have an image which is not a wave signal. It's the windows of a European building, maybe a cathedral or something, whatever it is. Because it's very counterintuitive, that's why I'm emphasizing it a lot. Even that thing is consisting of linear combination of wave functions. All right. So some number, it may be a complex number, of course, alpha, let's say, times this wave function, plus another number times this wave function, plus another wave times this wave function. We have a lot of rotated and with different frequencies wave functions, all orientations and all frequencies may be available because it's an infinite summation or an infinite integration. But when you combine them, they will give you this image. And I find it fascinating. Look at that. These waves are homogeneous. They are the same all along the space. But when I add them up, magically, when I add them up with the correct scales, of course, when I add them up, magically, it will give me an image which is not a wave. Can you imagine that? Or can you believe that it's a combination of waves, 2-dimensional waves? Look at that image. But it does correspond to combination of 2-dimensional waves. And these alpha, beta, gamma, all these coefficients are actually the Fourier transform values. So some of them, whether alpha or beta or gamma or whatever, it's a continuous variation, of course. Some of them are large, okay? They have larger magnitudes, and some of them are small. When they are large, it means that coefficient is prominent in your image. That's why you may want to remove it if you are, if that is a defect, for example. If this wave is a defect, then you look at the Fourier transform FUV, and you try to mask it, band reject it at this band, at the corresponding U and V, which are essentially omega-1 and omega-2 according to our notations. Okay, you find that point and you make it 0. You just band it, you stop it, you mask it. So knowing the Fourier transform of a shape of an image is a good thing. By the way, the Fourier transform, this one, excuse me, this thing, if you plot it along the omega-1 and omega-2 axis, they will give you alpha, beta, gamma values individually along a 2-dimensional axis. And they will look like this. the Fourier transform of this image is this. Of course, only in magnitude. So there are a few things. Let us focus to this, or maybe both of them. There are a few things that I notice when I look at the Fourier transform of it. The first one is, I will remove it later, erase it later. Along this axis, I can notice some intensity. I can see a horizontal line in the Fourier transform. Why? Where does it come from? What makes that line, horizontal line? Or let me draw it and keep it. Where do they come from for this image? They come from the perpendicular direction edges. Because if there is an impulse along the horizontal slice of the image, when you cut the image horizontally and look at the profile, if there's an impulse, that will give you ones. So it looks like that one. So where are those impulses or edges that appear when I cut the image horizontally? They are, of course, the edges that are perpendicular to this one, which are here, 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 here. I'm just emphasizing these edges. Okay. I'm trying to draw all these edges just to emphasize. There may be multiples of them. So all these vertical edges, when you cut them, they will make impulses or sharp variations along the horizontal direction. And that sharp variation along the horizontal direction will give you this horizontal emphasis. So when I see this kind of a line, I visualize it, I can understand that in my original image, even without knowing, I can understand that there are vertical edges. So it may be a building, because in the buildings, the windows or the doors, etc., or the buildings, their own edges will have some vertical sharpness, some vertical edges. So I understand that there are vertical edges on this. Now, another thing that I want to show you with a different color this time. I can see this tilted emphasis that I draw as a green line. I can also see another one which is not more vertical, but this is a little bit tilted from the vertical one, that one. What is it? Where does it come from? It comes from this edge, and probably yeah, actually it comes from only that edge. They are perpendicular to one another, okay? The green here is 90 degrees to the other one. Of course, with the normalizations, etc., it may not be exactly the same angle, because maybe this magnitude Fourier plot is plotted a little bit distorted in a different proportional ratio. Now I will ask you this one. It's more vertical, yeah. Where does it come from? From the image. Where does it come from? Do you have any suggestions? You can just say verbally, and I may try to understand what you mean. The yellow Fourier transform line that I can visualize and see with my eyes. What may be the reason of that in the image? No answers? Okay, then I will show you. It's coming from here. It's more horizontal. And when you cut it, the 90 degrees perpendicular of that is expected to appear. As I say, this Fourier transform is probably a distorted version of the original. Maybe the original image was 640 by 480, okay, width and height, whereas the Fourier transform is 512 by 512. So, of course, the angles may not match exactly, but in theory, the Fourier transform of a line, of an edge in the original image must be 90 degrees perpendicular to that one. Because when you cut this line that I'm showing you in this direction, along this direction, it will make a sharp variation, something like an impulse. So you see something like this, an impulse like that along this direction, which makes in the Fourier domain a uniform intensity along the same line. That's why every line will show another line in the Fourier transform, which is 90 degrees perpendicular to that one. For instance, if you want to blur or eliminate, blur, let's say it like that, some of the edges, but not the other ones. You can do some funny things with this one. For example, you want to eliminate the vertical variations of the image while not eliminating the horizontal variations. Okay, that's something that you may want to do just for fun. Then what you can do is, in other words, you want to blur out all the red edges that exist in the image. What you can do is, you can reject or mask this portion of the image, except the central one, okay? You must keep the central portion because it gives you the overall intensity of the image, that central portion. But you may remove the other portions of the strip, make them zeros, and you will notice that the horizontal, the vertical edges of the image suddenly became blurry, like the one you see at the right-hand side, which is a blurry image. But that blurry image is obtained by low-pass filtering the whole image. This was the center point. So this much frequency is passing, and anything beyond that frequency up to pi is rejected or masked. Therefore, we don't have such details or sharpness of high frequency components. Therefore, the image became blurry like this. Now, technically, if you are going to do something like this, you will notice that this center pixel here, the one pixel here, is exceptionally larger than the other ones, because that is the total intensity. It's the summation of all the pixel values. So if the image is large, the summation of all pixel values in grayscale will be a very large number. And it's very difficult to visualize it. So you may want to draw it in decibels magnitude, like taking the logarithm, so that extreme large values will be suppressed, or you may deliberately remove only the 0 by 0 coefficient, remove it, and plot a surface or an image-wise representation of the rest of it, and don't put the center pixel, because when you try to put it, it will make the image intensity so unbalanced. Like the center pixel is 1 million, the other pixels are 10, 12, 89, 15, etc. And when you try to visualize it among a million, they will be so dark. The rest will be so small and dark that you will not notice any detail. I bet all the money that I have, which is not much, to the fact that the Fourier transform that you see here was plotted using a decibel compression, where the center pixel intensity is not kept as it is. So a logarithm of all the intensities are first taken, and then it is being plotted. That's only then it happens like this. And since you will have a lot of take-home examinations and things like that, I will ask you to experiment something on your computers and plot it. Of course, a digital plot, I mean, just a PDF file or whatever. But I don't want to see a black image. So be smart about how to make the best of your explanation by plotting that explanation. If you have a huge number and all the others are so small that I cannot see them, it doesn't make sense. Okay, it's valid for all types of situations. Now, the last one is the high pass version. It's just the opposite. The central portions corresponding to the low frequencies are masked and they are gone. And the rest is retained and the inverse Fourier transform is taken and you only come up with the details. Look at that. You are only observing the variations, the details, but you don't have the intensity. For example, inside the windows, it's supposed to be dark. But darkness and lightness is a low frequency attribute. Therefore, you cannot observe them. You are only noticing the variations and the changes in intensity. That's a high pass filter. Notice that high pass filter does not mean a sharper image. It is sharp, but you wouldn't really like to have this image as a sharper version of the original image. So how do you sharpen an image now? Let's do some image processing, some practical. Let's think practically. How would you make the original image look a little bit sharper? Only look sharper, it's not sharpening. Okay, we're not, because we're not increasing the information. The information of the original is there, but you want to you want to fascinate other people by saying that my image looks sharper. Okay, that is a processing technique sometimes you use. How would you try to make this original image look a little bit sharper? Any suggestions from there? If you give me this image, I would say that it doesn't even look like the original image, or yet alone sharper than that. It's not acceptable. So what would you do? Any suggestions? Well, okay, I can recommend two ways, which are the same way, actually, different implementations of the two ways. First of all, if I call this X, image X, if this is Y and this is Z image, technically, theoretically, and of course, practically, X is equal to Y plus Z. Y, call it uppercase Y, and let's call this one uppercase Z. Y, capital Y plus capital Z is capital X. Okay, they are just reciprocals of one another. If you add these last masked Fourier shapes, capital Y and capital Z, you will come up with the original Fourier transform shape, capital X, which is telling me that X is also Y plus Z. To recover the image, what if I make an X hat, another one, which is like Y plus 1.2 times Z. So I increase, I emphasize the high pass coefficient, the Z coefficient, a little bit more, 1.2, not 1 times Z, but 1.2 times Z. Then, as you see, the details will be more emphasized and you will come up with a crisp or a sharper looking version of X. It's not sharper, but it looks sharp. Or on top of the original X, you can make a perturbation like this. X double hat is equal to X plus 0.2 Z. So x double hat is like this. And I can say that x hat is equal to x double hat. So you can either add the some small portion of the high pass version to the original, or you may increase the high pass version and emphasize it more than the low pass version and then combine them together to come up with a sharper looking image. Okay, that's how you obtain sharper images. Another nice example. This is exhibiting some periodic structures. We have some periods horizontally and vertically too, because the width of the bricks are also repeating themselves. Now notice that, let me make it red to make it visible. The period of the brick horizontally is wider, okay? Therefore, the corresponding Fourier transform along the horizontal axis will exhibit faster repetitions like these red stripes that I'm trying to show. Okay, the separation between those lines are narrower because the brick is wider. Whereas when the brick is, or maybe I should use a different color. When the height of the brick is narrower, the yellow separation I'm showing, because of that, we are experiencing a wider separation in the vertical direction. But I can notice those ripples. These ripples, like sink-like shapes, correspond to a periodicity in the original image. Just by looking at this Fourier transform, I can guess that the image is something like this. If you didn't give me the original image, my guess would be like this. Something like this. But look at the original image. The brick positions are not aligned. But I cannot resolve it from here. From here only I can resolve this much. I cannot guess how much each brick is shifted to the left or to the right because I don't have the angle term. So this angle of FUV is not given to me. Only the magnitude is given. And from that much magnitude, I can guess that the image is consisting of wide bricks. And I can just tile those wide bricks like this and say that maybe the image looks like this because I don't know the phases. But with the phases, the bricks may be tiled correctly. Of course, you cannot take the inverse Fourier transform of only the magnitude to come up with this image. The image information also requires the angle. In fact, there is more information in the angle than the magnitude of the Fourier transform. And we have a very nice experiment to do that. I strongly recommend that you do it. It's like this. Take one image of a person at the same size. Let's say a small image, 128 by 128 image of, let's say, a person, okay? And the same size of an image of, let's say, a house. Okay, here it's the house, and here's the sun. So this is the house, and that the red one is the person. You take, let me use black. The Fourier transform of it to obtain, let's call that image X, the magnitude of X of omega 1, omega 2, and the angle of x, omega 1, omega 2, okay? And from here, you take the Fourier transform to obtain y of omega 1, omega 2 in magnitude and also in angle. In MATLAB, you can easily do this using FFT in 2 dimensions. And the angle and magnitudes can also be recovered easily using simple mathematical tools such as MATLAB. And then, no, this one is not, of course, x, it is y. I'm sorry. Magnitude of y and angle of y. Then, since these are just numbers, right? Complex numbers in general, let me construct a new set of numbers by, let me say, combining the magnitude of x and the angle of y. And assume that my new z has a magnitude of x and an angle of y. So it's like x times, or magnitude x times e to the j angle of y. It's a new complex number. You construct it like that, using the magnitude from one and angle from the other one, and you come up with capital Z, and take the inverse Fourier transform of that one, and you will come up with an image. You should better take the real part of it only, or the magnitude if you wish, I don't know. Because you may come up with some complex values. So get rid of those complex imaginary parts. Just focus to the real part and try to plot, show the real part. What will it look like? So I take the magnitude from the face image, person, and the angle from the house image, merge them, took the inverse Fourier transform, and look at the image. The image looks like what? Actually, I already told you the answer, but you may just try to give me an answer here. Anything? There are two options. It either looks like the face, or actually there are three options. It may look like the face, it may look like the house, or it may look like nothing but noise. So which would be your preference, your guess? Still waiting. Please, one of you just open the mic and tell me something. You know, when you watch the videos, sometimes I will put them on the internet, you will laugh at yourselves and say that, you know, the professor was talking to nothingness and we were not listening. Haha, that was me who didn't answer. So don't do that. Hello? Are you there?
Yes, I'm here.
Yes, you are there. Then tell me.
Yes, I'm here, but unfortunately,
But you don't know the answer. But there are only three options. Just say one of them. Would it look like the information coming from the magnitude of the Fourier transform, or the phase of the Fourier transform, or none of them, but it will make a noise, or whichever? What would be your guess? It's just a wild guess.
it can be magnitude of the transform.
Yeah.
Magnitude. Or say,
we are
yeah,
only
magnitude of the transform.
Excuse me?
Magnitude of the transform.
Magnitude.
Magnitude, yeah.
Because that's what we are looking at. We are looking at the magnitudes of this transform. The plots that I'm drawing, they're all magnitudes. So they contain a lot of information. That's kind of correct, but it's the wrong answer here. That's why I wanted you to give me the wrong answer so that I can say the correct one. It actually comes from the phase, because the phase information contains the variations or the changes in the intensity. in the original coordinates. So coordinate-wise speaking, the information is carried in the phase. It is also contained in the magnitude, but the magnitude, for example, would make these bricks darker, and the connections of these bricks lighter, like this one, the image itself. The phase is not aware of this darkness and lightness, but it is aware of the changes in intensity. So the image will really look like this one, the house. But the intensities will be different, but the variations of the house will be visible, and you will see nothing from this face image if you do it this way. So the image properties are actually carried in the along the phase. That's an interesting observation. Let me see. Let us see some applications, and these are important. I know that we are running a lot out of time, but these are so important things. This is exactly the technical or practical implementation that I was talking about. If you come up with this kind of fingerprint, the fingerprint here is contaminated with too much noise, which is undesirable because it makes detection algorithms fail, which is the tissue here that you have, the texture of the cloth. So let us try to remove those cloth textures from the image. How can we do that? We take the Fourier transform and look at it. Notice that there are speckles, some peaks that are periodically repeating themselves. They come from the periodic texture of the cloth at this, at these positions. I don't want to make it yellow, but I want to make it white this time. Okay, like this point, this point, this point, this point, etc. We don't want them because they belong to the texture. So we just need to remove them. How can we remove them? We can just remove them as we see it on the Fourier transform. We mask them with the black dots that appear here. Those black dots means they are masked with very small filters. Okay, they are not a low pass filter, they are not a high pass filter, they're nothing. They are just a filter to remove these dots in the first image, to remove those peaks, speckles. We are removing them one by one by masking, as we see here. And when we take the inverse Fourier transform, we have significantly reduced the effect of the cloth, as you see. That's this is image processing. So if you say someone, tell someone that you have taken image processing courses, they may request that you know image processing. These are the fundamental, essential things that you must be aware of. If you say you know image processing, then you know what to do with the image for the improvements, for their improvements. This one here has horizontal lines or vertical waves that appear. It's actually horizontal lines, which is a defect, maybe due to the paper that the image is taken on. So how can we remove those lines? We take the Fourier transform. Notice that there are dots like this. So we have to mask them because those dots are because of the impulsive periodic pattern when we cut the image vertically. So we mask them, we remove those points, we make them zeros, we mask them with very small, tiny band reject filters. The black portions here are passing, and the white dots here are the stopping regions. We stop, we take the inverse Fourier transform, and look at that. We have eliminated mostly the horizontal lines. while not affecting much the rest of the information. So the information is still visible. By the way, this has been done in 1966, really on lunar orbital, because they had only analog photography over there. They did not have digital photography or anything. So when they take the picture, they saw this. When they printed the picture, this defect was there. So how can you eliminate that defect using analog processing techniques? Or you can scan and make it digital. This is what you are expected to do. The magnitude versus the phase, this is one important thing that I was talking about. The phase looks like this. And I don't know if, yeah, here is the thing. If you take the phase, the example was already here all along. So I was trying to explain an example which was available. If you take the phase from here and the magnitude from the other one and combine, this is the image that you get. And in here, I don't see the right-hand sided image, but I can see the cathedral image. The properties of the cathedral image are there because of the phase. Conversely, if I take the phase from the right-hand side image and take the magnitude from any other image, I come up with this ugly-looking image. Of course, it's not very clear, but I can see some visual hints from the right-hand side version of the cathedral image. So this was what I was trying to tell you all along. We have a lot of examples of that by combining phases and magnitudes. For example, the phase of this image, I don't know, it must be a Japanese character or something. You see that the similar features are available at the right-hand side, and the left-hand side more looks like the building, because the phase information comes from the corresponding places. Okay, I think we are well out of our time, so I should better stop at this point, but let me give you a word if you have any questions. You may collect your questions and ask me in the beginning of next week's lecture too, if you wish. And for the next week, I will try to inform you from this week's Canvas module or the next week's Canvas module. Just check all of them all the time. I may give you the link to this PDF file from Oxford University. It was, I guess, was it? Yes, it was the Oxford University, as the name suggests. I'm not familiar with the authors. I hope I'm not violating their copyrights for 2014 notes that they made public, and now we are recording it, and I will make them public again on YouTube probably. But yeah, that's what I will do. So anyway, any questions? If you have no further questions, I will stop the recording now, and we will meet 9:30 next week, Tuesday. Until then, take care.